Hello, my name is Chengjie Huang, and this is my seminar presentation for my PhD project, VADet, multi-frame LiDAR 3D object detection using variable aggregation. This presentation is based on our published work, published in WACV this year, 2025, with the same title. So in this presentation, I'm going to go over some background information on relevant topics such as LiDAR and 3D object detection. Then I'll introduce the method we developed called VADet to address some of the challenges in 3D object detection. I'll present some experiments and results we have on various datasets, and then discuss some limitations and potential ways to mitigate those limitations. So LiDAR sensor, LiDAR stands for light detection and ranging. It's a sensor that's used to measure range, hence the name. And typically a LiDAR sensor will contain three major components. First of all, we have a laser, which will shoot out laser beams aiming at specific target. A receiver, which will detect the light bouncing off the target. And a processor, which will process the signal and compute the range based on the time of flight of the laser beam produced by the laser. So this way, a LiDAR sensor can accurately measure the range from the sensor itself to a particular target the laser is aiming at. Now, this type of sensor is very widely adopted in autonomous driving scenarios for two main reasons. First of all, it's able to produce accurate range measurements directly, as opposed to, let's say we want to get the range from a camera image or a stereoscopic camera images. Typically we'll use heuristics or other ways to estimate the range. But in the case of a LiDAR sensor, due to the way the sensor works, we can get that range measurement directly and more accurately compared to cameras. And secondly, because LiDAR sensor is an active sensor, it actively emit laser beam and then detect the laser beam that's bouncing off the target. It can operate in low light conditions without much problem compared to camera sensors, which the effectiveness will diminish when we have lower and lower light conditions. Typically in autonomous driving scenarios, the laser sensor will produce a 360-degree point cloud like this. The max range in the commonly seen models will range from 75 to 200 meters. But the downside is, compared to camera images, we have a very low vertical resolution, ranging from 32 to 128 beams, which will cause a problem that the measurements for long-range targets and long-range objects will be very sparse. So in our work, we're interested in particular 3D object detection. And this is a task of identifying and locating objects in 3D environments, which will involve, first of all, classifying what type of object is present in the environment. We want to determine the location of the object in terms of a 3D XYZ coordinate. We want to determine the dimensions of the object, the length, width, and height. And since it's in 3D, we also have an additional degree of freedom in the yaw and heading of the object. So compared to 2D object detection, wherein typically we are only interested in a XY and length and height of the bounding box. So the bounding box in the 2D object detection case will be axis aligned. The 3D object detection bounding boxes are they have more degrees of freedom. Now, because of the problem that I mentioned earlier, the nature of the LiDAR sensors being very sparse vertically, and also the fact that the detection will get sparser and sparser the farther you go, 3D object detection directly from LiDAR data can be very challenging for those objects with sparse point clouds. Either they're very far away because of the LiDAR sensor, or because they're occluded by some other objects. For example, this vehicle behind this truck is partially occluded, and you can see that the shape of the object is kind of not complete, and the point cloud is sparser than the other objects in front of it. So to address this challenge, a commonly adopted technique for 3D object detection is called point cloud aggregation. In this technique, we simply want to concatenate consecutive 3D point clouds and to enhance our current observations or make the point cloud denser using consecutive frames. And this is practical because in practical applications, autonomous driving, for example, the point clouds are collected in sequential order. So more precisely, let's denote a point cloud collected at a particular timestamp tau as p sub tau. And just to note that the point clouds collected by the sensor will be centered around the ego vehicle or centered around the sensor, which will move along with the ego vehicle. So here's an example of that, where we have the ego vehicle approaching a four-way intersection from a timestamp tau minus I to a current timestamp tau. So you can see that the point clouds will look very different. Now, if we simply aggregate those two point clouds without any other steps, we'll not get very much information, or will not enhance what we want, but rather we'll get a kind of a messy point cloud with various duplicated features. For example, this building in the background is duplicated twice in the aggregated point cloud if we just use simple concatenation. And that's because the point clouds, again, are centered around the ego vehicle when they're collected, but the ego vehicle is moving, so we need to kind of correct that motion from the ego vehicle. So to do that, we first want to represent the ego vehicle motion, and that's typically done using a ego pose, which is in SE3 space. So it's a 4x4 matrix. And for each timestamp tau, we will have a different transformation matrix representing the ego pose at that timestamp. And what that matrix is representing is basically a transformation from the ego coordinate system to a particular and arbitrary common global coordinate system. Sometimes they can be determined by, for example, the first frame of the scene of the sequence of point clouds, or it can be determined by a GPS coordinate system. So to do this, taking a previous point cloud where our ego vehicle is still approaching the intersection, p sub tau minus I, we basically want to apply the ego pose transformation, basically transforming this point cloud from the previous coordinate system, the local ego vehicle coordinate system, to a global coordinate system, and then back to the current ego vehicle coordinate system. So that's why we're multiplying the t sub tau minus I with the t sub tau inverse. And then if you compare to the current p sub tau, where the ego vehicle is inside the four-way intersection, you can see that the background features, which should be stationary, they are now aligned. And more generally, we can generalize this process to aggregate more past frames using the same transformation. And then in the end, we can just concatenate all the point clouds after the transformation. And what this will give us is a very densified point cloud. But as you can see, the background features are very nicely aligned, and they're densified, which will make certain objects easier to detect. However, because this motion correction is only addressing the motion from the ego vehicle, it's not really accounting for the motion from other dynamic objects. So what we observe in this process is that for those stationary objects, they are typically, this process of aggregation works very well. Those objects are densified and they have more complete and more accurate geometry because of the aggregation process making the point cloud denser. But for dynamic objects, because we're not accounting for the motions of those objects, the point clouds of those objects will appear very distorted and it will appear as a smudge. And this will cause difficulties for object detection. And from our preliminary experiments, we found that there's a huge performance trade-off when we simply aggregate a point cloud with a fixed number of frames. So as we increase the number of aggregated frames from 3 to 16 in this case, we'll see that the stationary performance, object detection performance in terms of average precision, is going up because of the more complete geometry and denser point clouds. But for dynamic objects, for example, the slow and fast vehicles, the performance is going to degrade as we introduce more frames because of the distortion that I showed in the previous slide. So this leads us to our method. To address this particular challenge, we introduce what we call a variable aggregation detection, VADet. So the main idea is to be able to dynamically aggregate each detected object according to its properties, such as the movement of the object or some other properties like the density of the point clouds. And just to give an example from the previous example, one way to dynamically aggregate those objects to achieve optimal performance is, for example, we do 16 frames for stationary objects, 6 frames for slow objects, and 5 frames for faster objects. Of course, this curve will look different depending on what architecture you're using, and it may even look different with different initialization, different training runs. So this will need to be dynamic and need to adapt to different architecture and different instantiation of the model. So to be more specifically, the way we do that is we assume that we have some previously detected object bounding box from a previous frame. We want to learn a particular function that depends on that object bounding box that will give us the optimal number of frames to aggregate. We call that function eta. And because that curve that I showed previous slide can very much depend on the architecture and how the model is trained, we learn this function eta empirically for each detector by performing an in-depth analysis of the performance over a wide range of input configurations. So given a particular model and that's trained in a particular way, we will feed that model different number of aggregated frames and analyze the performance for different types of objects. For example, we will look at the performance for slow versus fast object. We'll look at the performance for dense versus sparse objects. An example of this is, let's say we want to analyze the performance for stationary slow versus fast object. We will feed a range of 3 to 16 frame input to the model, and then we can determine what's the best aggregation strategy for a particular type of objects. In this case, the number of frames in the red circle will correspond to the optimal aggregation strategy for particular type of objects given a particular architecture. And similarly, we can do the same thing for other factors other than speed. In this case, I'm showing the analysis for objects with different density. We have sparse, medium to dense objects, and as you can see, there's also a similar, albeit slightly less impactful trade-off. Now, a challenge we encountered during this process is because we need to feed that model a wide range of input configurations. Traditionally, what we would like to do is to train a separate model for each configuration. Otherwise, if we just train a particular model on 3-frame input and feed that model a 16-frame point cloud, we will get some degradation in performance, but that's not because of the trade-off between different types of objects. That's just a domain shift from 3-frame input, which the model is trained on, versus what we're providing it, such as a 16-frame input. So to accurately assess this performance trade-off or wide range of input configuration, we want to be able to train a wide range of model using each configuration. But that's really computationally intractable. You need to train a lot of models using different number of input frames, and then analyze the performance for each object for every single configuration. Additionally, like I mentioned before, even if you use the same architecture, different training runs and different initialization could result in slightly variation in the trade-off curve and in the performance. And those are the two main challenges with regard to this, how we want to construct the eta function. So what we end up doing instead is we propose a training technique called random aggregation training, or RAT, in which we want to train a single model that can handle multiple input configurations at once. So in the end, we can just evaluate that model using different input. And this is done very simply by randomly varying the number of frames per scene during the training. And then because we have an increased variety in the training input, we also want to increase the amount of training to compensate for that. And in the end, we found that if we train the model separately using different number of frames, compared to we train a single model but using the random aggregation training, the performance trend is consistent. So that was how we constructed how we learned the optimal number of frame function eta based on a previous input. Now here, I want to talk about how we construct the actual point cloud based on what we know about the previous object and what we know about the eta function. So first of all, because the object can be potentially moving, the object may not be stationary, we first want to estimate the region of aggregation for that previously detected object in the current frame. So we want to estimate where the object might be in the current frame without detecting it accurately first. So for example, let's say we have a moving vehicle here. In the previous frame, we observed that as a bounding box here, what we want to do is to, having a current frame P sub tau, we want to roughly determine where the object might be based on what we know about the object in the previous frame. And to do that, we first estimate the object center using basically a fixed velocity model. The object detector will provide us with a velocity estimation for each bounding box, and we can just assuming that the object is moving at the fixed velocity, which is typically a valid assumption because the time interval between each frame is very small. But because the object could be moving, and as I presented in one of the previous slides, when you have moving objects and when you aggregate multiple frames, the point cloud will appear distorted. So it will have a smudge behind the object due to the object motion. And to include that smudge, we also want to adjust the bounding box dimension so that after aggregation, we not only aggregate what we think the object is, so for example, in this case, the green box represents the true object size. But because this object is moving, we want to aggregate not only within the true object bounding box region, but we also want to include the trailing smudge, the distortion from motion as well. So to do that, we basically want to adjust the bounding box dimensions and the center position based on, first of all, the number of frames and also the velocity of the object. So these are the formulas that we use to roughly adjust for that and to include all the distorted points. So after the adjustment, we can just crop and aggregate each object from all the previous frames. This is a very simple and straightforward process. And in the end, here's an example of what the result might look like. From left to right, we have the 3-frame input, which will appear very sparse, especially for those stationary objects on the top, which are occluded by this bus over here. And the 16-frame input, which is very dense, including even the ground points, they're extremely dense. And for dynamic objects, you can see that we have a very distorted point cloud with long smudges behind the actual object. And for VADet, we can see that, first of all, on top for those stationary objects, in 3-frame input, they are barely visible, but after the variable aggregation, because they're stationary, our algorithm assigned them to have a higher number of frames, so they appear very dense, even though they're technically occluded by this bus over here. And similarly for those dynamic objects, because we determined that they're fast moving, we're not really aggregating a lot of frames and not including all those distorted point cloud, which could potentially hinder the accurate detection of those objects. So that was basically the general idea of our method. So now I'm going to present some experiments and results. For experiments, we use 3 representative 3D object detectors. They represent the voxel-based, fully sparse, and transformer-based backbone for 3D object detectors. Specifically, we're using Centerpoint from CVPR21, VoxelNext from CVPR23, and DSVT also from CVPR23. And using those different architectures will demonstrate that our method is really architecture agnostic. It doesn't really depend on the specific design, and it works in general for multiple architectures and backbones. For dataset, we're choosing the Waymo benchmark. It's a very large-scale autonomous driving dataset developed by Waymo, formerly a Google company. It's collected mainly in San Francisco, Phoenix, and Mountain View. It has a lot of LiDAR frames, over 230,000 LiDAR frames with over 12 million 3D boxes. So it's a very large-scale dataset that can accurately evaluate, help us evaluate the performance of our method. So first of all, I want to present some overall performance in terms of average precision. And first of all, this is the baseline comparison between the VADet method versus all the fixed input configuration method. Just to note that because we're evaluating over a wide range of input configurations, this is not coming from individually trained model, but this is from a single model using our random aggregation training strategy. But as you can see, for all 3 architectures, the VADet can outperform any of the configurations, even the best ones, ranging from 12 to 15 frame for Centerpoint and VoxelNext, and 16 frame for DSVT. And similarly, we can compare it to other state-of-the-art method on the validation split, and we see that using 3 to 16 frame input, we can also outperform the state-of-the-art two-stage detectors such as 3D-Man and MPPNet, both using 16 frame input. Now on the test split, our method also outperforms pretty much all the state-of-the-art published work. What's interesting is that we also noticed that our method can achieve better performance than even camera LiDAR fusion methods. And this just highlights how much the performance trade-off, addressing that performance trade-off can give us a large performance boost. Now, before I mentioned the plot I showed, I was showing a trade-off between stationary, slow, and fast objects for different number of fixed aggregation frames. Now, in this table, we can see that for VADet, our strategy is able to achieve the best performance for all types of objects, regardless of how many frames we're using. And that's thanks to the adaptive nature of our method, which will adjust the number of aggregated frames based on the type of object. And similarly, we see the same trend for point cloud density. There's a small trade-off between different objects with different density, and the VADet strategy can dynamically adapt to those situations and achieve the best performance. And here's the qualitative result. Same example that I showed before. Again, with 3 frames, some objects could be very sparse, some could be occluded, but if those objects are in fact stationary, they will be densified and they will become much easier to detect. And for 16 frame, the fast-moving dynamic objects are going to be very much distorted, and they're going to be very difficult to accurately locate, as shown by the detection here, which is offset from the ground truth box. But in VADet, we're not aggregating that much. Another benefit of VADet that we hypothesized that could also benefit the detection performance is because we're not aggregating the background points. Some objects that are denser could become much easier to detect compared to if we aggregate everything at once. And this can be seen by this example here where we have 2 stationary objects here, stationary vehicles, parked on the side. They are aggregated 16 frames and they're dense objects, but they're not actually detected accurately by our detector. And we hypothesize that's because of the interference from the background points that are also aggregated very densely. But in our case, because we're not aggregating the background, we're only focusing our detection on the foreground objects and aggregate those foreground objects. So our work has a few limitations. First of all, because the VADet, like I mentioned, we assume that we have a previous frame prediction to bootstrap or to determine the region of aggregation for our current frame point cloud. When we start the algorithm, we need to bootstrap our algorithm, and in our case, this is done by simply running a normal detector for the first 3 frames, and then gradually we'll start aggregating more and more frames. And the other thing is, because VADet doesn't really try to utilize the past point cloud to their fullest, we'll simply limit the number of aggregations so that we don't over aggregate and we don't cause distortion that can be detrimental to the object detection performance. We still cannot really effectively use past point cloud to determine the location or the class of the current point cloud or the objects in the current point cloud. And this is particularly the case for fast-moving objects, where, as shown in the previous example, we're not really aggregating that much, which means we're not really using any of the past information. And this can be addressed by some other more involved method that try to utilize those past point clouds in some other ways. And finally, VADet also require a predetermined function which we call eta. And in our work, we specifically focus on the speed and point cloud density properties. But there could be also other properties that we are not testing or we haven't thought about to construct our function eta. So in the future, in an ideal situation, the eta could be entirely learned without some predetermined properties such as speed and point cloud density that we kind of hand determined using data analysis. And that's it for my seminar presentation, and thanks everybody for listening.